My talk is trouble with typed racket, try contract profile. This little thing, if you don't know what this is, then you haven't seen the classic 1967 episode of Star Trek, The Trouble with Tribbles, in which the Starship Enterprise was invaded by just a few of these cute, furry-looking creatures at first, and they were harmless, and they were adorable, and everybody loved them, until they started multiplying, and eventually the entire starship was taken over by tribbles, and nobody could get any work done, and they had to send them all away. And it was very sad. So I like to think of types kind of like tribbles. When we have an untyped program and we let in types, it's like, what's the worst that could happen? You know? They make our code cuter. They make it easier to understand what's going on in our code. They give us these guarantees about like common errors that are caught. They're just like good things to have in our code until we have to enforce those types at runtime. And then we end up like Captain Kirk here, up to our ears in runtime contract checks. But there is something that can help us out, which I'm going to tell you about today, called a contract profiler. And the contract profile package is what has this tool and can be really helpful. So in this talk, first I'm going to go over with a small toy example what exactly the problem is and why it happens. And then I'm going to put on my programmer hat and show how you, as a developer, a racketeer, if you encounter this problem, what you can do to make things better. And then I'm going to put on my researcher hat, and I am going to kind of pick apart the process that I will have told you about and ask from a researcher's perspective, how good is that process at making things better? All right. So this is our toy example. Basically, we have this sub1 function that we wrote ourselves that is untyped, and we have this typed module that does the exact same thing, except it has a typed version of sub1. You know it's typed because I put a little picture of a tribble in the top right corner. And it's just, it's just for integers. We'll just say it's a sub1 integer to integer. All right. And so in our toy example, we have this third module that imports both the typed version and the untyped version. And we have this until 0 function, which basically just applies f until as many times as it needs to until the result is 0. So it just says f, 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 f until we get 0. And so in this code that runs it at the bottom, basically what we're doing is we start at 1 billion and we sub1 1 billion times till we get to 0. And we're doing that with the typed version of our sub1 and the untyped version of our sub1. And so now, if you'll notice, we also time how long it takes to do each one of those. So let's see what those timing results are. So it turns out the version that uses the typed version of sub1 is way, way slower than the untyped version. And so what's going on here? So basically, what's happening is any type that can't be verified at compile time and taken away is converted to a runtime contract check. And so basically, that typed sub1 function, not only is it subtracting 1 billion times, it's also checking that its input is an integer 1 billion times. So we are getting like 1 billion of these type checks, a very simple type check, but in this case, but it just all adds up, and we get this huge slowdown. And I also want to show you what happens when things are reversed. So when I add types to this main module, and I'm going to keep the same typed and untypedness of the other two, I'm just adding types to this main, what we see is that these numbers flip. So earlier the red number was on top and the green number was on bottom. Now the typed import is very cheap and the untyped import is very expensive. So basically the way to think about this at a higher level is this concept of boundaries. So a boundary is an import-export relationship between two modules. It doesn't matter which module is importing the other module, we're just going to call that a boundary. So when you have a boundary between two typed modules in your program, things are happy. If you have a boundary between two untyped modules, maybe you're a little less happy because you don't get the love and joy that you could have from using types. But like, at least your code is still pretty fast. But when you have this boundary that transcends typeness and untypedness, where either we're importing from typed into untyped or the other way around, that's where this trouble starts. All right. So you might be saying to yourself, this example was kind of pathological. I was literally subtracting 1 from a billion times, and I was doing nothing with that result. Like maybe in real programs where you're actually doing some useful computation, there will be more work that the computer actually does besides type checks, and it will kind of balance out more. And this little bit of type checking we do is going to be worth it. So a lot of members of the Racket community have studied this problem in the very strongly named Is Sound Gradual Typing Dead paper in 2016, and its JFEP follow-up. Here, they looked at around 20 different Racket programs in the wild, in the real world, and they studied, one of the things they studied was if we add types in really pathological ways, what's the worst that can happen? So there's nothing about the actual code itself that like in our toy example, was causing things to go wrong. It was basically this is just a problem everywhere. And in certain cases, it can get really, really bad. It can get to not just 10 times, but 100 times, 1,000 times, and so on. All right, so what can we do as a programmer, barring any advancements in the actual language side of, are there ways we can improve the sound gradual typing implementation? As a programmer, say that we have a program and it's behaving badly in this way, what can we do to make things better? And so one of the things I want to propose to you today that is a really useful tool that I found to make this better is the contract profile tool. So what is the contract profile tool does? Basically, it's a profiler that organizes the costs in your program that come from executing contracts. So it tells you this contract that corresponds to like this, it's wrapped around this value in your program. This is the approximate amount of time that you're spending evaluating that one same particular contract. So in order to demonstrate how to use this tool, I'm going to use the JPEG library, which Andy Wingo wrote the untyped version in 2014, and Ben Greenman added typed versions of all the modules in it around 2020. So we'll be able to look, and it'll be very easy to type a module because Ben Greenman has already done the work of actually writing those types. We just need to hit a button, and boom, we can have a typed module. So let's start out with all of our modules untyped. JPEG has 5 modules: bitports, EXIF, Huffman, JFIF, and main. And Ben Greenman, in addition to adding types, he added a driver that basically just like runs the functions on a given input and times it. So just like in our toy example, we'll be able to see timing information. So when we run this program, our initial time is 135. And we are going to kind of use this time as, as a marker. So basically, all our times are going to be relative to this type that we initially get from the untyped program. And basically, we're going to say, it's a simplification, but we're going to say if our code runs faster than this, it's a fast program. If our code runs slower than this, it's a slow program. So the first thing we need to do is type a module. I'm going to throw a dart at the screen and see where it lands. Oh, look, it landed on this JFIF module. Let's type this first. All right, and now I'm gonna wave my magic wand, and boom, it's typed. All right, so let's see what the timing information is like now. So we got a 2-time slowdown for this. I mean, that's not terrible, but that's not very good. What can we do about this? So let's use the contract profile tool. And, oh wait, sorry. Okay, so basically, first, what are our options, basically, if we're in this situation? So our first option is we can remove the types that we've added, but if we had actually added those types, it would have represented a lot of work and a time that we put into doing that, and we don't want to do that. Maybe we should tell Typed Racket to ignore our types at runtime. The static type information will help the compiler a little bit. Maybe we can do some intramodule optimizations, but we're going to lose a lot of the type soundness properties. It's going to make debugging more difficult. This is also not a good solution. Third option, we can accept the slowdown. Obviously, that's not good. And I want to propose something counterintuitive. I think we should add more types to our program. Why? Remember, it's these boundaries between typed and untyped code which are leading to this massive slowdown that we don't like. So if we find a really costly boundary like this, and we convert it to a typed boundary, then we get rid of the slowdown, and as a bonus, we now have more typed modules in our life, and who doesn't love typed modules? There's a problem though, and that's that there are 2 possible candidates in this case for boundaries. So in this code, JFIF imports from 2 other modules, Huffman and bitports. So we need to make a decision about what to do next. Contract profiler, the contract profiler, this is where that comes in. It'll tell us where to add types. So basically what we do is we run this incantation in our terminal, Reiko contract profile, and we get this result. So what does all this text mean? The first thing is it'll tell us the amount of time that our program spends executing contracts. It also tells us what the most costly contracts are in our program, ordered to from most costly to least costly, and what the approximate amount of time is being taken up by each one of them. So if you look at this column, you can see that the first 2 contracts are taking up more time than any of the other contracts in the program. And so it turns out that these first 2 contracts come from the same boundary in our program. If you look at the text over here, we see that this JFAF module and it's the Huffman module is where these other functions are coming from. That's kind of the boundary that's taking up all this time. So if we type this boundary between Huffman and JFIF, then maybe our problems will get better. So we should type huffman.racket. I'm going to wave my magic wand again. Boom. All right. What is our timing like now? Now we're at 2:14. That's That's better. I mean, it's not great. We started out at 135, and so it's still slow relative to that. It's still slower than it would be if we didn't have any types at all. So it's not great. We should keep going. Let's use contract profile again. All right, let's do it again. Same deal. This one contract at the beginning is taking up more time than any of these other contracts. Where is it coming from? It's coming from this boundary between bitports and Huffman. So now, let's type bitports, magic wand. Oh. There it is, there it is. The magic was a little slow. All right. So now, we actually have a really fast time, 34. And notice that we didn't have to type every single module in our program. We only had to type 3 of them. And so this workflow that we followed is we ran contract profile, and we basically, to make it more general, what we did was we added up the cost of each boundary, and we added types to the boundary that was most expensive. And so yeah, this workflow sped us up, but I also want to note that it did it monotonically. We just got better and better and better from where we started at 325 until eventually we reached something that was faster than our kind of signpost for what we consider to be a fast program. So now I want to switch my hat from programmer to researcher, and I want to kind of interrogate this implicit claim that I've been making that the contract profiler can help us speed up our program monotonically. And so basically what I'm going to ask is this workflow, does it actually work? And to do that, so I'm going to define this concept of a configuration. So this workflow sped us up monotonically when we started from this untyped, 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 typed, untyped configuration, where JFIF was the one thing that was typed, that was our starting point, and we're able to get to a good place monotonically from that. But there are a lot of different possible configurations we could have started out at. JPEG has 5 modules. Each one can be in a typed state or an untyped state, so that's 2 to the 5th, 32 configurations. And if we look at those configurations, we see that 24 of them are slower than untyped. So there are kind of a lot of different bad places we could have started out at. So I want to ask this question, does this workflow work on these 24 configurations? And to do that, I'm going to define this term success threshold to be what is the speed of the untyped program. And more precisely, the question I'm going to ask is how often does the workflow we followed guide us to this success threshold monotonically? All right. So in order to kind of formalize this and run this, answer this question in the form of an experiment, I am going to have to add some more specification to this algorithm. First, I'm going to have to add a stopping condition because we don't want it to just run forever. So I'm going to say let's stop whenever we reach a good speed or when everything is typed, because at that point we can't do anything else. And there's also this edge case here. I mentioned costliest boundary, but the thing is, contract profile, it doesn't always have output. It doesn't always have output that, like for example, sometimes it will tell us that the boundary we really need to worry about is a boundary between one of the modules in our program and one of the modules in a library. In that case, for the sake of the experiment, I'm going to consider everything in a library as kind of the outside world. And so we're going to say that in this case, where this is the only boundary that's identified, it's not really something we can take action on because we may not even have a typed version of that library that we can just like wave our magic wand on. So I'm going to say that If such a boundary exists, add types to it. Otherwise, we'll just pick a random boundary that's inside our program and add types to it. So this is our final workflow, and we also need something to compare our workflow against. So we're going to define a baseline workflow that basically just always picks randomly. So in order to see if contract profile is helpful, we're going to have this other workflow that doesn't use contract profile at all. It's just going to always pick randomly. And basically our question is, do we get better than this baseline? Do we get better results? And so I'm going to run these tests across 16 different benchmarks. Most of them are from the JFP paper I mentioned, and a few stats. It ranges from 4 to 10 modules, which means 16 to 1024 configurations, different authors, different styles and features used. So it's not perfect, but the idea is that we can kind of get a sense of, in the real world, how well does our workflow with contract profile work. So these are the results. Basically, on the left is our workflow with contract profile, and on the right is our baseline workflow. So the thickest bar at the bottom represents our monotonic success rate, and the thinner bars on top, the first one represents what happens if it represents the success allow monotonicity to be broken once. So basically, does it ever guide us away for one configuration, but then after that, it's just everything is faster and everything is good, to get a little more insight into what's going on. So what do these results tell us? Basically, it tells us that contract profile, this workflow I described, it does help us a little bit, but it's only 6%, the difference. So in a lot of cases, you might be totally fine just picking a boundary randomly. So what is the reason for this? So there are kind of a couple different reasons. The first one is that when we type a module, we're getting rid of the boundaries that the contract profiler told us about. But we're also introducing new boundaries to other modules that we didn't know about before, that we had no information about, how expensive would those boundaries be if it was between a typed and untyped module. So the contract profiler, it's kind of a heuristic that can help us make a good guess about what to do next, but it can't always just tell us what is the perfect next step we should do, because our next step could always lead us into a trap where suddenly, there's tribbles everywhere and there's just nothing you can do. All right. So there are also some cases, however, where the contract profiler kind of just gave empty output. And so kind of the next steps in my research are I'm going to try to investigate these specific cases on these specific benchmarks and kind of try to see what's going on. And hopefully, I'll be able to bring a new, improved contract profiler to the racketeers. But for now, it's still better. Using contract profile can help you, but it isn't perfect. So in conclusion, Trouble plus Reiko contract profile is fast, happy code most of the time. And you can read more about the contract profiler in Vincent's dissertation and the docs for the contract profiler. And you can read more about the experiments my collaborators and I did in these papers. One thing to note is these papers also add a lot more nuance in terms of examining more than one profiler type, so not just the contract profiler, but what if we try to simulate the contract profiler's behavior with other profilers? And it also expands the notion between, instead of just we have like untyped code and we have typed code with the natural type semantics, what if we also have the transient type semantics? Can that help us find a good, are we able to find kind of somewhere in the middle using transient types and the contract profiler together? And just a taste of that paper, I'm not going to explain this chart, but basically what you need to know is that the workflow we explored is right over there. It still wins out. So yeah, thank you.
All right, first question.
So why is monotonicity the right metric? If you looked instead at, by the end, what percent of modules I had to type, would the contract profiler look any better from that metric instead?
Yeah, I think what's important about monotonicity is kind of the psychological element to it. If I'm using a tool and it makes it does something bad and then it does something good, I might give up on it after I see it do something bad. And it's not really a fun guarantee to think, oh, well, eventually it'll make things better for me. If monotonicity is kind of like one way of doing it, and it kind of includes this element of effort. But yeah, one of the other things we looked at a little is like how many modules do you have to type? Because like that's also important. But monotonicity, it kind of, it takes that question away a little bit and instead like kind of helps focus on like what's like the immediate things that are happening.
Okay, and do you have any rough sense of what often the answer is on how many modules you have to type? Like, it feels to me like, especially with this metric of we want to get as fast or faster than untyped code, how often are you just having to type everything?
So it kind of varies by benchmark, and that's another reason that we stayed away from using number of modules is because, if a benchmark has like 14 modules and another benchmark has 5 modules, like what does it really mean from, like how do you really aggregate that data and get a good picture of like how many modules on average are you typing? And what was the second part of your question?
Just like how often do you have to type everything to reach your threshold?
So that's another interesting question because the answer is sometimes you type everything and it's still worse than untyped because you're using maybe untyped libraries. And so most of the time there are quite a few. Like I think like around half the benchmarks definitely have places that are like not completely typed. But I'm not actually sure because like that's also including a world where we have the option of using transient types. In this world where we only have natural types and no types, I'm not sure what the answer is.
Thanks.
Right. Well, you have a question? Yeah, sorry. I noticed that when you can't find a good boundary to work next, you pick randomly, like the baseline strategy.
Yeah.
And maybe this is just see the paper for details, but are there more sophisticated find the best boundary than take the top line result of the contract profile output? For example, I might, with a human brain, look at the couple of top results like we did in the example with JPEG and sort of aggregate some of those together to decide where to look next.
Yeah. Yeah. It definitely, like, we definitely tried a lot of different strategies, but most of them were based on this notion of like finding one boundary and doing that. But yeah, I definitely think that's an interesting direction to go.
And I'm curious, does the choice of the first one, where you don't have any information, that's just completely random, right? So the first module, the first boundary that you...
And that's why we want to look at, we want to find all of the configurations where it's slow, and we want to average across all of those configurations. Is what we're not just, we're looking at the entire set of possibilities of where we could start out, and we're kind of treating each one of those equally.
Hi, William Bowman from University of British Columbia. So I was interested that both of the approaches that you talked about, pick randomly or use the contract profiler, they're both online, they're both dynamic. You are always running something and trying to pick. But I feel like if I was staring at a giant code base thinking about porting it to Typed Racket, the very first thing I would do is kind of offline try to come up with a plan. And I wouldn't pick randomly, and I wouldn't want to run the contract profiler on a whole bunch of different scenarios. I would probably, I don't know that I would really do this, and I don't know that it would be effective, but I would probably think about, okay, where are lots of boundaries happening? And where are those boundaries under loops or recursive functions or something? So I could try to predict where the most expensive boundaries were. Did you investigate anything like this?
No. Kind of the purpose of our experiment was really to evaluate the contract profiler itself in this context. So we kind of kept very simple our thoughts about like the alternatives to the contract profiler that we use and like static methods. Yeah.
Hi, I'm JJ from the University of British Columbia. This might be kind of a stupid question because I don't know much about Typed Racket, but the typed to untyped boundary being expensive makes a lot of sense. But the untyped to typed boundary doesn't make as much sense to me because it seems like you're already losing out on a lot of guarantees that types give you in your main module. I was wondering if you could talk more about why you want to keep those guarantees around for external modules, and like, I guess just that, yeah.
So in the context of like, so if we look at, so you're saying like this first example seems like something we would want to do, but the second example doesn't seem like a place where, so like where we're importing, sorry, can you repeat like the two cases you mentioned?
Yeah, like you don't have types in your main module here. So like, why do you want types at all, I guess, in external modules if you don't have them for your full program? It seems like you would lose out on kind of a lot of guarantees that all of types give you. So I'm just, I don't know much about how Typed Racket works, so I'm wondering why you want to keep those around.
So you're asking why we would want like any of our modules to be typed if our main module isn't typed? Yes. I guess,
Do you have something you'd like to add to that, Alex, or are you asking a different question? Just wanted to, okay, different question, sorry, go ahead.
I mean, you want to make sure like that module is doing what you want it to do. And like if you have the power to like verify that, it's not like inherently a bad thing. But yes, like there is kind of like a difference in that trade-off. It's not like a uniform trade-off all the time, depending on the context. But we do kind of like treat everything equally. So yeah, that's a good point.
All right, so we are running low on time, but okay, we're gonna eat time away from our break, and I don't know if anyone has any special preferences on that, but I think it's fine. We can probably just eat away into the break. That should be okay. What do you think? Yeah, that should be all right. All right, let's start with Alex here, and then I'll run over to you. Oh, yeah, the same question. Okay.
So the reason that you get, so I think there's two questions that you're asking. One is, why is it expensive if you have an untyped module being used in a typed module? And the answer there is just that because Racket is a higher order language, we can export functions, we can export higher order functions. So we have to do the same kinds of potentially expensive contract checks at boundaries in both directions. And then as to why you would want to make different choices about what modules end up typed, it all depends on like what your goals are for typing. I mean, it might be that your main module is just a simple wrapper and all the important work is going on in some other module. It might be that one particular module is where you really want optimizations or strong guarantees, or it might be that you're engaging in the kind of process that this talk is all about, which is incrementally moving from one place to another on that spectrum. And you might have decided for whatever reason, maybe just that's the one first in alphabetical order, that's the one you were going to tackle first. And so that's how you ended up in that particular situation with that particular kind of configuration.
Of course, Sam would have the answer to that question. Alex.
So a lot of this is for running the contract profile on a mixed program. Mm-hmm. Are there any benefits to running it on a completely untyped program? Like, is there a contract you could just attach to anything, like any RAP-C on all exports that would give you a hint at what boundaries are the most costly before you even do any work typing any of them?
We haven't looked into that. Right now, all of our work has been focused on like contracts from types. And I don't think, so you're saying, sorry, could you repeat your idea?
When there's a typed untyped boundary and there's an any type, there's a particular contract used there called any wrap/C. And maybe that's going too far. Maybe just a one-layered version of that.
Oh, so you mean instead of like when we have module by module typing, when we have like dynamic typing that's associated with like individual values?
Yeah. If you had just starting with untyped modules, but adding like the simplest contracts just on everything, not knowing what the types are yet, would that give you hints at what boundaries would be most costly before you even go into the work of typing a single module? Yeah, I think that's a really good idea. Like, because then you wouldn't have to like put in the actual effort of figuring out like exactly like choosing the types, but you could still get like kind of a sense on a practical level, and it would be like from like a real run of the program of like which types would you call the most? Yeah.
Okay, we're going to wrap up now, but I'm Ben. I want to just give a huge thank you to Nathaniel. You saw there were two papers at the last slide of the talk. One paper did not have his name on it. The other one did. The one that didn't have his name has so many bugs, like a dozen bugs in how we ran the experiment, bugs in the code. There's nothing to fundamentally change the conclusions, but it's been a heroic effort, and thank you, Nathaniel.